Okay, good morning, everyone. I'd like to welcome you to this morning's webinar. It's the first in a series of 3 for the NextGen RoadFuels research project. This is a very exciting research project in which lots of the consortium are researching on how to change urban waste into a valuable, to upgrade urban waste into a feedstock that can be used for as a biofuel that can be used for road transport. Today we'll be hearing from Joscha, Irantzu and Thomas. Thomas will be giving us an overview, an introduction into the project and also today's presentation. And then Irantzu and Joscha will be talking a bit more in depth about some of the research that's been taking place. Before we hear from Thomas, I'll just say some housekeeping rules. Please remember to keep your microphone on mute throughout the presentation. And if you do have a question, please write in the question box. Please do not use the chat box because the chat is just for saying hi, etc. It won't be monitored for questions. But if you use the question and answer box that you'll find at the bottom of your screen, then our presenters will respond to your questions at the end of each of their presentations. Or they'll write to your response, but I think it would be better if we talk it through. Okay, so thank you very much for joining us this morning, and we'll hear now from Thomas. Thomas, the floor is yours.
Thank you, Emma. And you can hear me and you can see me. And you can see my presentation.
Yes. Thomas.
Thank you very much.
Perfect.
All right, so thank you for the introduction, Emma. And as you mentioned, I would brief you about the NextGen RoadFuel project in general and dig a little bit deeper into the scientific outputs on a helicopter perspective. And then we will dig deeper into the different aspects in the coming presentations in this webinar and also in the coming webinars in the series. So today I will start talking about the NextGen RoadFuels project overall. So the idea of the NextGen RoadFuel project is to convert urban wastes into ultimately road transport fuels. So what you will see here on the left-hand side is an overview of the roadmap of the project. So we're looking at different urban feedstocks, particularly sewage sludge, which will be the topic of these webinars. But we also are looking into other types of urban waste, such as construction wood and food waste. Now, dealing with waste is also dealing with different technical challenges. And so the first step of the project is to look into how do we get these feedstocks and how do we pre-treat them in the way that we can process them and in a way we make maximum value out of it. This is what Irantzu will be partly talking about in the next presentation. Then in this project, the core technology is called hydrothermal liquefaction. And for those who is not familiar with hydrothermal liquefaction, it's a wet process, high temperature, high pressure process operating at the near critical point of water. So plus 350 degrees, plus 220 bars. And we make use of the moisture in the wet feedstock to break down the macro structure polymers in the bio mass and turn it into a biocrude that we can then further refine into finished transport fuels. So I will talk briefly about some of the achievements, particularly in the HTL, a little bit about the upgrading and where we're going next. And then Joscha will take you on take you deeper into the HTL. If we look at the consortium, the partnership, we're 12 partners, well distributed over Europe, representing the total value chain from biomass, feedstock, through HTL, through upgrading, and all the way to markets. As you can see here in the bottom, we have been running for more than 3 years in a out of the total 4 years. It means that we're coming to an end. And now what we would like to is to disseminate some of these outcomes in a series of webinars. As you might see here, I represent Aalborg University, which is also the managing university of the project. Then on board we have Deeper Energy as an innovation lead, and now Emma represents ETA Florence as the dissemination lead for the project. Just an overview of what to expect. So what is already in the calendars today's webinar, where we will brief you about why we think HTL can radically change the way we think about wastewater treatment. As Emma mentioned, we have Aalborg University here, KIT and CENER. Then in mid-March, we will be hearing about how we can set up techno-economic analysis of this process train and calculate mass, energy, flows, and ultimately economy. So we get an idea about what is the cost of this technology. And then also in the calendar, we have a third webinar by, I mixed it up here a little bit, sorry for this. The next one is actually by SINCEF. The last one is by KIT, looking at how we can treat the aqueous phase coming out of this process, because we get a lot of water. Water is a liability, it's costly, and we are on the track to develop new methods for how we can treat this aqueous solution. All right, so let's get an overview. Some of the things we have achieved today is presented in this slide. So Irantzu will dig a little bit more deeper into the pre-treatment, but the thing about waste biomass is that they contain a lot of nitrogen. Nitrogen can be valuable, but for fuels, it's not very valuable. So part of the pre-treatment is to see how can we actually extract this nitrogen so it doesn't impede the process is coming down in the process train, and at the same time make value out of it. So one of the things we've been looking into is to see, can we extract proteins, amino acids, and thereby make value out of it? And indeed we can. We have demonstrated that more than 75% of the nitrogen can actually be removed in a pre-treatment step. Now, after pre-treatment, when you have the biomass, we perform the hydrothermal liquefaction. As I said, we have been running different feedstocks. Now, the scope here in this series of webinars is the SLUDGE. And on the right-hand side, you see the pilot unit at Aalborg University, operated in collaboration with Deeper Energy. And what we have demonstrated is the processing of more than 8 tons of sewer sludge. And when you process sewer sludge, you get different products out of it. Joscha will talk more about it, but one of the valuable products is, of course, the liquid that comes out, which is this biocrude that you see in the right lower corner. This biocrude is not a fuel in itself. It's oxygenated, it's nitrogenated, it has lots of pollutants, minerals that you have to deal with before you can actually upgrade it into finished fuels. One of the main tasks of this project has actually been to develop the next stage, so the stage between the biocrude and the upgrading, and to understand what it actually takes to turn the biocrudes into an upgradable step, so it can be fed into standard refinery equipment. I believe we have achieved so. We have recently produced more than 100 kilos of upgraded biocrudes. In essence, it has all the nice parameters: low viscosity, low microcarbon, low mineral content, low water content, and it is indeed upgradable. My colleagues from Aalborg University have demonstrated that we can easily run this in a fixed bed hydrotreater for several hundreds of hours. Then what else comes out of it when we're dealing with urban waste is that we really want to valorize the whole package that we get. So we're not just getting carbon, we want to turn it into fuels. We also get a lot of phosphorus and other minerals that we have to take care of. We have demonstrated that we can make a solid product as a byproduct that contains more than 95% of the phosphorus that is on the input material. Now we know already now that the phosphorus recovery is not what's going to change the economy of the process, but indeed in the circular thinking, this is a value proposition, and it could also be a key enabling for the coming legislation for phosphorus recovery, especially from wastewater. Yes. Another value proposition of HTL is the high temperature. So we know that when you get waste, you get things that is not just carbon, but it could be micropollutants such as pharmaceuticals, but also microplastics, and something we have been looking into in the NextGen RoadFuel project. Now, we have investigated an assay of different pharmaceuticals. And as I said, we're processing here at 350 to 400 degrees, which means there's a natural hygienization process going on. And for more than 20, I think 25 pharmaceuticals we have probed, we have seen that we have a nearly complete destruction of all these pharmaceuticals. Now, what is new is that we've also developed a method to quantify and qualify the microplastics, which is in the sludge, and also where it ends up in the effluent streams of HTL. So with a combined analysis of microscopy and FGIR analysis, we have developed this method that can quantify microplastics, so in terms of polymer type, but also in a size distribution. What you realize is that there are many types of microplastics in the sludge, but the good thing is that most of those are prone to degradation at high temperatures. So what we have seen is that if we take sludge and microplastics, about 99% of the microplastics is actually destroyed in HTL. What remains is a little bit of polyethylene, a little bit of polypropylene, which is kind of expected because these polymers are not prone to thermal degradation. But the good thing is that they end up in the fractions that is not going back to the farmer's field, for instance, in a solid product with all the phosphorus. Now, digging a little bit more into the aqueous phase, because when we get with feedstock, we get all the water. We have to discharge the water. When dealing with wastewater from HTL, we're dealing with concentrations several orders of magnitude higher than what you typically see in a wastewater treatment plant. This is what you can see here in the diagram in the upper right corner. It means that we cannot just discharge it to nature, for instance, and we cannot just recycle it back to a wastewater treatment plant because of its concentration. So we have to deal with it on site. One of the things we have been looking into is a thermal distillation of the wastewater. So to keep carbon in a concentrate that's so it doesn't pollute the water, and the same thing with nitrogen. Now, of course, doing thermal distillation comes with a cost, but the good thing is that we can retain most of the carbon in a concentrate that can be recirculated back to the process. This is what you see here on the lower right-hand side. The first bar here shows the energy efficiency from biomass to biocrude. If we do no recirculation of carbon, and we are above 60% of energy recovery. But what happens is that if we start taking all the carbon we lose to an aqueous phase and bring it back to the process, we can actually achieve more than 85% of the energy recovery, which is pretty good, I would say. So we're good in recovering the phosphorus, we destroy all the micropollutants, we keep the energy in the biocrude, and this is also equivalent to more than 70% of the carbon that goes from the biomass to the biocrudes. We're also looking into different types of aqueous phase valorization that will be part of a next webinar. I will just quickly touch base on it here. This is developed by KIT, a series of filtration and membrane distillation units. And the idea is that you're dealing with a water phase, which is very inhomogeneous, suspended solids, minerals, everything that will clog downstream operation. Now, KIT have demonstrated that with With an ultrafiltration setup, which is being aerated, we can actually retain all the solids in an aqueous phase, but at the same time also recover ammonia. So much of the nitrogen in the feedstock turns into ammonia that we can recover in the setup. And to this date, we have demonstrated that more than 90% of the ammonia can also be recovered from this aqueous phase. Now, the membrane distillation, the primary scope of the membrane distillation is to remove water that can be discharged. And at this point, we have demonstrated that at least 60%, up to 70% of the water can easily be recovered. Ali and KIT will talk more about the details. But the good thing is that they can actually maintain a high flux of these units, which is really what you need to drive down the cost. But this will be the scope of the third webinar. When you have the biocrude, you need to upgrade it. You need to hydroprocess it to remove heteroatoms such as sulfur, nitrogen, and oxygen. Now, in the project, we are dealing with different technologies, such as electrocatalytic hydrogenation developed by the Technical University in Munich. And then we also dealing with more, say, standard refinery techniques, such as fixed bed upgrading. Now, this is a joint effort of different partners: TUM, Steeper Energy, CPRI in Greece, and Aalborg University. I'm not going to give you detailed information about the outcome of this yet, because we hope that there will be another webinar in the series that will talk more about this. But as I said, we have demonstrated that we can run a fixed bed hydrotreater for hundreds of hours. And I hope that we can present these results to you later on. Now, the final thing we would like to do in the project is to finish the value chain. So as I said, we produce the biocrudes, we can hydroprocess them to turn them into hydrocarbons, finished fuels that we can further distill into market products such as gasoline, diesel, and jet fuel. Now, what remains in that value chain is, of course, to demonstrate that these can be brought to market and can be either combusted in an engine on its own, or it can be mixed with the fuels we already have on market. So over the next 3 months, we will be looking at different aspects. So how these biofuels, upgrades, blends can be mixed with market fuels, and what are their emission profiles when combusted. So what you see here on the diagram is 2 different approaches. Once we have the HTL biocrude, we can distill it and turn it into distillates, which are still oxygenated and nitrogenated. We know from previous experience that these distillates are not miscible with standard fuels, but they can be blended in to an extent. And so what we would really like to see is what are the physical blending walls of these fuels, and when are they in compliance with the standards on market, such as the EN 590 and the ISO 8270. The other thing is that we would like to do is to take the biocrude that we have already upgraded and distilled. So now we have hydrocarbons with minimal heteroatoms. We can distill them, we can mix blends, or we can take the bulk upgraded biocrude and mix them with, for instance, bunker fuels, marine diesels, or road diesels, and perform the engine testing. And as I said, the project is not over yet, but over the next 3-4 months, we're going to do the engine testing. And I hope that if you stay tuned, we will present to you also a webinar on engine testing. All right, I think that brings me to the end of the overview of the project. We're doing many more things than that, and I hope that you will stay tuned and have an eye of the coming webinars, not just what's in the calendar, but also what should be in the calendar. All right, Emma, thank you for that.
Thank you, Thomas. We have a couple of questions for you from Mr. Leone. The first question is, do you first extract FOG from sewage sludge?
No, we do not.
Okay. And his second question is, 100 kilograms of biocrude from 8 tons of slurry is a question.
Yeah, you know, these numbers do not match. That's true. So the 8 tons of, so the fat, oil, and grease is something that's being extracted in the wastewater treatment plant. We just get the sludge. Now the 8 tons is not equivalent to the 100 kilos of biocrude. The 8 tons is just how much that actually ran through our pilot units. Now in numbers, about 40% on mass of the organic content in sewer sludge turns into biocrude. So that is really the figure of merit that you have to look at, not 8 tons to 100 kilos.
Okay.
But 100 kilos is what we have produced in upgradable form.
Okay, thank you, Thomas. That's very clear. I hope that's clear for Mr. Leone. Okay, great. Perfect. That's a lovely introduction. And now we're going to hear from Irantzu for a slightly more in-depth look at some of the research.
Hello.
Thanks.
I'm going to try to share my screen. Please let me know when you see the presentation.
Yes, we can hear and see you clearly. Thank you.
Okay, so thank you very much for the introduction. My name is Irantzu Alegria and I work at CENER, at the National Renewable Energy Center located in Spain. And this presentation is more focused on the composition of sewage sludge, because we would like to have a deeper look at the components of the sewage sludge, yeah, and how it can have an impact over the process of the HDL process that comes later. Yeah. So therefore, the title of this presentation is the composition of sewage sludge, the key to its utilization. Yeah. This presentation shows the results of 3 different sewage sludge, which comes from Denmark, yeah, located from a city located of Aalborg, located in the north of Denmark, that covers a population of around 200,000 people. And this sample is quite peculiar because it has been delivered in the form of pellets, so therefore the moisture content is quite low, it's below 8%. Yeah. The second sample comes from Germany, from the region of Baden-Baden, from Karlsruhe, that covers a population of around 300,000 people. It's a primary sludge that is being subjected to a centrifugation in order to increase the primary content, and this sludge is later being used for incineration. And the third sample comes from Spain, from the north of Spain, from a small city named Tudela, that covers a population of around 40,000 people, and also collects water from the agro-food industry that is in the nearby. Yeah? And this treatment plant has a treatment filter as a secondary treatment, and the sludge is being the water goes through a screw. Yeah? So in order to have
sorry, Irantzu, I've just had a couple of comments that your voice is a little bit quiet.
Oh, sorry.
That's okay. Thank you.
Okay, I will try. Yeah. Yeah. So the analysis that has been performed to these 3 samples are moisture, ash content, volatile content. We have also performed the elementary analysis. We have also determined the carbohydrates and lignin content. We have also determined the extractives, lipid and amino acids. Yeah, because we wanted to see where remain the main difference or similarities between these 3 samples. Yeah. So if we start with the water content, yeah, the water content makes a difference. Yeah, I have already mentioned that the sample of Aalborg has been delivered in the form of pellets, as can be seen here in the picture. Yeah, and on the other hand, the sample of Karlsruhe and Tudela are delivered with a high water content, up to 70 or even up to 80%. Yeah, so there are quite a lot of differences between the samples depending on the wastewater treatment plant process itself, if these sludges are being subjected to an aerobic digestion or to incineration or to agricultural purposes. We have also looked the difference in terms, for example, of ash content. It's quite significant, the difference between these three samples in terms of ash content. Yeah. For the sample of Aalborg, the ash content accounts up to 38% more or less. Yeah. And in case of the Tudela sample, is less than half of it. Yeah. The other one is in terms of volatile content, the sample of Tudela has a higher content, almost up to 78%. Yeah, and in case of the Aalborg sample is much lower. Yeah, then something similar happens to the carbon and hydrogen content. As for the macro elements, yeah, we would like to point out to remark the amount of phosphorus and how it's presented combined with in salts with calcium, forming calcium apatite, and also in combination with iron, forming imbibing it and extending it. Yeah, it is also relevant the amount of silica that is found in the form of sand, that may come in the form of sand or minerals. Yeah. We have also looked for heavy metals for the sample of Aalborg and Karlsruhe, yeah, and only for copper, nickel, chromium, and zinc. Some amounts has been found, but in any case, all these values are much below the limits that has been established or indicated in the SEWAGE sludge directive. So if we move on to the organic fraction, we have looked for the carbohydrates content and also into the lignin content. Yeah. As for the carbohydrates content, which is shown in in the blue columns, we can distinguish between the hemicellulose content and the glucan content. Yeah, it is these values varies from 10% for the sample of Aalborg and Karlsruhe up to 17% for the case of the sample of Tudela. Yeah. When we look into the lignin, which is the class on lignin, the values of lignin can be as high as 20% for the sample of Aalborg, yeah, down to 7% for the sample of Karlsruhe. In between stays or relies the sample of Tudela, which accounts for around 30%. We also wanted to know which the amount of soluble or water soluble content in these three samples, yeah, and also the extractives in ethanol. Here in the bright orange column are some the amount of water soluble components of these samples, yeah, and once more we can see that there are big differences between the three samples. Yeah, in the sample of Aalborg, the water soluble content accounts up to 8%, whereas for the sample of Karlsruhe, it can be as high as 20, or it can be account up to 23%. Yeah, in this sample of Tudela stays in between with accounting up to 30%. Yeah. As for the ethanol extractives, there are also it can be seen there are some differences between the sample once more. Yeah, the Aalborg and Karlsruhe samples accounts for around 8%, whereas for the sample of Tudela, it's much higher. It covers around, or it accounts around 23%. And that can be related with the total lipid content of the sample, yeah, because we saw that the lipid content of these samples can vary quite a lot. Yeah, and not only we look for the total lipid content, but also we determine the amount of fatty acid content, yeah, for the sample of Aalborg and Tudela. It can be seen here that for the samples Aalborg and Karlsruhe, the total fat lipid content accounts for less than 10%, whereas for the sample of Tudela, it accounts for almost 28%. But not only that, from this total lipid fraction, around 60% is in the form of fatty acids, yeah? Whereas from the sample of Aalborg, only 20% of the total lipids are in the form of fatty acids. But that can be answered because of something that I have already mentioned, that is that in the nearby there is an agro-food industry. If we look deeper into the fatty acid profile, we can see also some slight differences, yeah, between the sample of Tudela and the sample of Aalborg. For the sample of Tudela, palmitic acid and oleic acid are the main fatty acids present in the sample, followed by dinoleic and stearic acid, whereas in the sample of Aalborg, the lineolic acid and palmitic acid are the major fatty acids, followed by oleic acid and stearic acid. If we focus on the amino acid content that has been detected or determined in this sample, once more we can see that there are big differences between the samples. Yeah, the Karlsruhe sample shows an amino acid content that accounts up to 22%, whereas for the sample of Tudela, it only accounts to 13%. Yeah, in the meantime, it's Aalborg accounts for around 16% of the by weight. Yeah, but it's not working to mention that in although there are some difference in terms of weight of amino acid content, the amino acid profile is quite similar. It's very similar between the samples, yeah. And being glutamic acid and aspartic acid, the main amino acids, followed by alanine and lysine. And when considering the total nitrogen content in the sample, the nitrogen content in the amino acid accounts for around 55% in the case of the sample of Tudela and 73% in the sample of Karlsruhe. Yeah. Another fraction of around 8 to 14% of the nitrogen is in the form of ammonia, and the rest of the nitrogen is in the form of organic compounds that can be can account from 16 up to 30%, depending on the sample. So in summary, the mass balance when considering this fraction, the lipid, amino acids, lignin, carbohydrates, water extractives, and us, accounts more or less to 100%. But there are some differences when only considering the lipid, the amino acid, the lignin, and the carbohydrates between the samples. Yeah, for the sample of Tudela, it accounts for up to 72%, but only for the Karlsruhe, it only accounts for 48%. So, having this into consideration, we were wondering what happens with these compounds during the HDL process, yeah? And even more, how these compounds may have an impact in the HDL process, or even more to the quality of the biocrude that is being produced, yeah? And we were wondering whether the interaction of lipids, proteins, and sugar may play a key role in the HDL process, yeah? So the answers to these questions will be provided by Joscha Zimmermann, that in a short time. Joscha.
Thank you, Irantzu. That was really interesting. We just have one question about your presentation from Ignacio Segura. The question is, what is the relationship between the specific fatty acids and the free fatty acid content in the samples?
We haven't determined the differences between the free fatty acid and the whole fatty acid. We have to determine it as a whole. Okay. We haven't distinguished between them. We have distinguished between total lipid fraction and the fatty acid content in this lipid fraction.
Perfect. Thank you. I hope that's sufficient for our participants. And again, really great. Thank you, Irantzu. And over now, Joscha, the floor is yours.
So I hope you can hear me.
We can see and hear you.
Perfect. Okay. Yeah, welcome to my part of today's webinar. As mentioned, my name is Joscha Zimmermann, and I'm a PhD student at Karlsruhe Institute of technology. And like my colleagues Irantzu, Thomas and Emma, I'm part of the NextGen RoadFuel project, which I'm grateful for as this is founding my research. In my research, I'm dealing with the nature of nitrogen in HTL biocrude oils. And today I will try to give a broad insight into what is happening during HTL and why nitrogen is an issue and how we can maybe face this issue. So now it's not moving. Okay. So, but first I will start with the water. What makes water such a useful agent to do the conversion of biomass into a fuel intermediate? There we have to look at the properties of water at elevated temperatures and under pressure. And this curve here on the left, the pressure to temperature curve defines more or less which process we want to apply. So we can go on also which product we want to receive. So we can go into a lower temperature regime, so to receive carbon material, and we can go into an elevated mediate temperature regime to receive a terry product, the so-called biocrude, or we can go even higher to receive gas like methane or hydrogen gas. We want to focus now on the terry product, the biocrude, so we operate our process between 300 and 400 degrees. And within this temperature range, we can see two important parameters changing. So the dielectric constant, this is called eta, is going down to a value round about 20, which is comparable with acetone. So suddenly non-polar compounds are solubilizing in water. And in addition, we also see an increase of the ionic product, the IP. So there is more dissociation of water into ions, the proton ion and the OH ion, which is alkaline. And this is supporting the autocatalytic effect of water because these ions are attacking functional groups of the biomass and hydrolyzing it and also promoting reactions. So when we condense it down in HTL, we depolymerize biogenic polymers. And simply said, they are lipids. Here on the left is a triglyceride, proteins, and polysaccharides. And here's shown a peptide, which is a fragment of a protein, and a polysaccharide from the cellulose, so glucose monomers. And we are cutting them down by hydrolyzation, but this is not stopping them because we are also other reactions ongoing. We have recombinations, we have condensations, cycle additions whatsoever. And in the end, we get stable forms, which are gaseous products, small monomers, and we have aqueous products, which are soluble and highly polar, soluble in water, and unpolar compounds, which are likely to be then the biocrude. And we have also these condensation and products and recombination products that end up in a char. So we want to focus on the biocrude, and this is then because we have so many reactions ongoing, more than 10,000 up to 20,000 different compounds. So we need to simplify the reaction scheme somehow, but later more to that. First, I would like to compare the biocrude with the fossil crude because so the petroleum, because we want to substitute it in the end. And petroleum is also a wide mixture of thousands of compounds. So we show here just the elemental analysis, and we see a difference in the heteroatom content, especially the nitrogen and the oxygen is really, really high in the biocrude. So we want to get in the end a fossil, not a fossil fuel, a road fuel or a ship fuel or aviation fuel, and that needs to fulfill specific industrial standards. And even with the petroleum, the conversion road would be, we go for distillation, hydrodesulfurization to upgrade the oil and refine it, and then get a fuel out of it. With biocrude is a little bit different. We need first to denitrogenate and deoxygenate the oil. Oxygenation is not the big issue here. Nitrogenation is the issue because it's not so simple to remove it from specific groups, because we have forms like amides where it's terminal. This is more or less easy, but when it's in a form like a heteroaromat where the nitrogen is found here in the aromat, it's really hard to get it out, to crack open the aromatic ring because it's stable. We really need harsh conditions and really effective catalysts. And there's still a lot of research ongoing to to promote these reactions. But in this talk, we focus on something more upstream to improve the sewage sludge, for example. So we can ask the questions for this talk: whether the N heterotherms originate, in which form the N heterotherms occur, and how does the origin of sewage sludge influence the HTL biocrude composition, and how can a pre-treatment improve the HTL biocrude composition. So as mentioned, we have a feedstock which consists of the three polymers, the lipids, the proteins, and the polysaccharides. And as mentioned before, there are a lot of reactions ongoing, but we can simplify that. For example, from lipids, we get free fatty acids and aliphatics, which are really nice. They are unpolar, they end up in the oil, and they are almost like a diesel fuel. But then we have also polysaccharides, which will end up in aromats like these ketones here, or in the aqueous, in short acids. But the purpose of this talk was the nitrogen. So we have a look on the protein, what's going on there. And we see that proteins, they hydrolyze down to amino acids, and then there's deamination ongoing. So we have amines, and they can react again with fatty acids to form these fatty acid amides. Also not a big issue. But here on the right side, we see the cyclization, the condensation, and cycloaddition, and also the Maillard reactions with the polysaccharides, or the sugars. And they are a problem because they form these aromats, and they are really hard to remove. So we heard from my colleague Irantzu before that different wastewater treatment processes result in sewage sludge with different composition. And we've liquefied these sludge samples, and we result also in different biocrudes, also different yields. And we see that the sludge, which was rich in lipids, consequently also result in a biocrude with higher yield and also lower nitrogen content. And the sludge here, for example, from Thessaloniki was rich in protein. It results in a much lower biocrude yield with a much higher nitrogen content. But comparing the elemental composition with each other is not that easy. So we put them in a Queveland diagram, which was first developed to evaluate solid coals or fuels like lignites or coal, but it also works perfectly fine for liquids. And we can see here on the bottom, on the upper left, the petroleum we want to get here. And here's our starting material, the sewage sludge. So by HTL, we're coming a little bit closer. And we see that the sludge, for example, from today, the green one, results in a biocrude which is much closer. And in the end, the upgrading has to do the rest to come to this petroleum fuel. For the nitrogen-related van Queveland diagram, the effect can be seen even higher. So the biocrude from Tudea was much closer to the petroleum than the other sludges. So now we want to improve the biocrude, and we already identified the protein as the compound that is polluting the oil, and we can upstream improve the biocrude by hydrolyzation processes, for example, with an enzyme or a mild hydrothermal treatment, as it is already used in some wastewater facilities to improve the digester afterwards. We want to hydrolyze the protein, solubilize it, and remove it from the sludge, and get then a better quality oil. So we did this. This is a two-stage process then. So we see that our sludge here, this was the one from Karlsruhe, had a nitrogen content of around 7%. And with water treatment at 150 degrees, we lowered the concentration of nitrogen down to 4.7. Consequently, also the amino acid content. And interestingly, the crude lipid content was increasing because they are not affected by the treatment. With the acid, we also used a really highly diluted sulfuric acid in a low concentration. This process can even be improved. So afterwards, we liquefied these sludges or these intermediates, and we result in a biocrude that has a much higher yield. So with the water treatment, we increased the yield by 8%, with the acid treatment by around 22%. And also, which is nicely to see, the nitrogen content is lowered by 22% and up to even 50%. And which is also improving is the composition, because we see more aliphatic species in the biocrude and much less heteroaromatics. And again, we can put this into a Van Geulen diagram. And as mentioned before, we want to come to this petroleum fuel here. And we see that with this upgraded sludge, we are coming by HTL much closer. So the sludge that was before used was the sludge from Karlsruhe. The sludge without the treatment would end up here, and with the pre-treatment become higher. And on the nitrogen related Van Geulen diagram, this effect is much stronger. So lastly, to conclude, we have N heteroatoms originating from a protein, and this in the interaction with lipids and carbohydrates. So proteins with lipids form long-chain aliphatic amides, which are meant to be not so problematic, but proteins and polysaccharides form these polyaromatic pyrules, pyridines, pyrrosines, which are aromatic and a problem in the end. And a lipid-rich low protein sewage sludge result in more biocrude with possibly higher quality, and the upstream hydrolysis is used to solubilize protein and then can improve the biocrude quality significantly. Yeah, thank you for listening, and I hope I can answer some questions.
Joscha, thank you very much. That was very technical and very thorough, really good. No, excellent. So we have two questions here. One is from Sarid Tor, and he's asking you, can you think of reasons why a wastewater treatment plant should invest in HTL technology?
Oh, this is a big question. I think this is not only a question for me, maybe also for Thomas. I think it can invest in HTL technology because we have the problem of sewage sludge, which is produced in a hell lot of amount, and there's a high tipping fee. So maybe we can get something useful out of it than just burning it like it's done here in the Western countries.
Great. Thomas, do you want to add to that? I
can do that. I will do that. I think Joscha is right. One of the things that I did not touch upon in my presentation is that in the project we made a big market study. And one of the things is, of course, legislation that we see in some jurisdictions. You're not allowed to bring sludge back to farm or fields, or you have to incinerate it and so on. And actually we made a study recently to compare HTL against mono incineration of sludge, and it's a more feasible business case. It's more environmentally benign. So I think there are many selling points. One of the other things is, of course, phosphorus recovery, nitrogen recovery in the form of ammonia, and the fact that you produce a fuel rather than it could be heat and power. So you're really maximizing your utilization of carbon.
Excellent.
Few selling points.
Absolutely. Yes. That, as I think Thomas mentioned earlier, there will be more webinars about this, the economic aspects. And I think some of our colleagues might touch upon the reasons why you would want to invest. Great. Excellent. So there's another question from Francesco Gentile. Have you tried HTL on anaerobic digestate? Who wants to answer? For Joscha, I think the question is.
Yes, we did this, but we can see it like this. If we do anaerobic digestion, we just removing carbon from the sludge that will end up as a fuel, as methane. But for an improved carbon balance of the HTL process, I think it's nicer to use not fermented sludge, because this is a little bit too deep into topic. the digestion of sludge is mostly used to lower the amount of sludge and not to produce much more energy from it.
Great.
Because in the end, we have to burn it anyway.
Yeah, exactly. Okay, excellent. Does anyone else want to add part to that?
Yeah, I think Joscha is right. I mean, we did process digested sludge, non-digested sludge, also the pellets that Irantzu showed in her presentation, and overall the conclusion is that you wanna maximize your utilization of the carbon that comes in with the wastewater. And if you don't do the digestion, you have just more carbon to turn into liquid fuels. But in the end, the process it still works on the different types of sludge.
Excellent. Okay, great. Let's move on to the next question. We have a comment from Felipe just to say that it's noted that microplastics and pharmaceuticals in wastewater treatment is a real problem in Europe and of course the world. So it's excellent that NextGen RoadFuels has started to respond to that problem. Thanks, Felipe. Okay, so let's have a look. Next question. Vicente Lopez. Question about pumping the slurry. Solid content feeding the HTL plant. What might that question be?
Should I take that one?
Yes, please, Thomas.
I think for sludge is really not an issue. One issue might be actually the dry matter content, because as Joscha mentioned, it's all about condensing and decreasing the volume of the waste. And so from a wastewater treatment plant, they can also decant the sludge and bring a sludge which has more than 35% dry matter. And when you reach that dry matter, it's actually semi-solid. So depending on which kind of pump you want to use, but it's definitely something that can be done. Now, I know this webinar is about sludge, but when we move into food waste, there might be some tricky things in the food waste you have to get rid of. Now, people throw their glass bottles, cans, and so on in there, and that you have to take out of the process before you feed it in, stones and so on, of course. But I really don't see the feeding in of the slurry as one of the technical challenges of HTL.
Right, excellent. Okay.
I mean, you can pump concrete to the highest top of a building. So
I can just add to that. It's easier in a bigger plant than in a smaller plant.
Oh yeah, definitely.
Excellent, great. Okay, another question that we have here from Mr. Leone. How energy intensive is the whole process?
That's a really good question, and he's
actually saying, can we produce a low carbon fuel with?
Yes.
Okay.
Yes, we can. I think in conclusion, yes, we can. That's not a problem, and actually, the energy intensity is also not the issue of the process. I don't want to spoil Gonzalo's presentation, but I think this is something he will touch upon. So maybe that's just a teaser to stay tuned with the webinar. Excellent.
Yes, I agree with you. Okay, and then the last question here, if no one else has anything, is about what are the applications for the solids? So you already touched upon that, Thomas. Is there anything else you might want to add?
No, it's really a fertilizer. It's a mineral product, and this is where we have all the phosphorus contained. So in a circular thinking, you just have to make use of that phosphorus. Yeah,
excellent. Okay, well, thank you so much, everybody. Oh, another question's just come in. This might be the last one. How do we deal with the heterogeneity in the feedstock when it comes to large-scale HTL? Doesn't the composition of sewage waste vary with respect to time and place and affect the composition of the final product?
Joscha, what do you think?
A big question.
I think this is a problem, but if we have for example, one big plant, for example, in Karlsruhe or in other bigger cities, the composition of the sewage sludge stays quite stable because it's more depending on the process and the area. But mixing different sludges from different areas in different amounts, I think, is not that easy. So this was also the purpose of our talk from Irantzu and me, to get a feeling about that.
Some variations and some differences from one period of time over the year, but still, there will be some, stable conditions that can be reached under for an industrial application.
Great, excellent.
Oh, another question.
And then we've got another question from Benjamin. Let's have a look here. So, is it more feasible to extract phosphorus from the solid residue, or really look for land applications of the solid residue overall? What about other pollutants found in soils, or in the solid, sorry. Other pollutants.
I think that is a really good question. If you look at legislation, so of course we also have heavy metals in the mineral products, but they are still below the threshold values of the legislation. So in principle, it could be disposed as it is. The question is, what is the bioavailability? Irantzu, maybe you want to join in, but as a biostimulant, it works as many other biostimulants. So that's not the problem. The question is more, can we make more value out of it by extracting it? And that is not something we have looked into in the project as it is right now. So the economics of it, I don't have a straight answer to that. But the biopollutants, we don't have pharmaceuticals, we don't have microplastics.
Yeah. I guess the key point regarding phosphorus is in the form that is, if it's in the form available for the plants, that would be interesting to dedicate some efforts into that.
Okay, that's a really good question, perhaps for another project. Okay, great. Okay, now it's 11:27, so we'll just wrap up here. Thank you so much, for our speakers and our participants. And I'll just remind everybody that the next webinar will be in mid-March, and it will be based on the economic analysis of this type of biofuels. So what's the minimum price we can sell this type of fuel for, fuel produced by HGL? So please stay tuned for your registration link, which will come out this week, and we'll see you again then. Thank you very much.
Thank you. Bye-bye.
Thank you.
Thank you.
Bye.
Bye, everyone. Bye.